We are going to start with periodic behavior of functions. Now, give you examples. When you listen to your favorite band, that's one example of a periodic function. If you are taking physics, grade 11 or 12, then you have seen probably examples of periodic function. For instance, electricity is one example, okay, which goes through the cycles. I'm talking about alternating current, not DC. The idling of a car, phases of the moon. The reason that these are periodic is that they happen again on a regular basis. For instance, 4 seasons, they follow a periodic cycle. Every year, the same thing happens. Now, it may be a little bit different, but the whole pattern repeats itself every year. This is why, they are periodic. And another important example is your heartbeat. I'm sure you have seen, in movies or somewhere, that the sine graph of a heartbeat when it's, showing on the screen. That's an example of a periodic, which means that it's repeating the same pattern over and over again. Now, these are all examples of what we call a periodic function. So the definition of a periodic function is a function which repeats itself. The pattern goes on and on. Now, periodic functions, they have some definitions that we are going to consider right now. This graph shows example of a periodic function which shows you the points of maximum and minimum of the function. For instance, these points are all the maximum points of the function, and these are the minimum points. Now, based on the maximum and minimum, I can define what we call the amplitude of the periodic function, which I'm going to give you the formula in a second. Also, if you look at the periodic function, the function goes through a cycle, and that cycle repeats itself. For instance, if I start from this point, you can see that the function goes through this, and then it ends up here, and then it repeats itself. We call this one period of the function. Now, period of the function, you do not necessarily have to take the maximum points. You can take any point on the function. If the function goes back to the same point, meaning the same y value, then we say that time is called the period of the function. Again, I'm going to show you the formula for the period. Okay, now let's go through a couple of definitions. We define a cycle as one complete repetition of a pattern. So in a previous example, I said if you start from this point and you end up here, this is called one cycle. Because after this one, the cycle repeats itself. And this is the pattern that you need. For instance, for a sine function, okay, when we start from 0 here, okay, we go to another point when the y value is going to be repeated. That's what we call the period of the function. Now, this part of the graph, which is going to be repeated all the time, is called a cycle, one cycle. If you have taken physics, then you are familiar with what we call frequency, which is the inverse of the period. We're going to talk about frequency in a second, so just hold on. We define a period as a horizontal length of one cycle of a graph, on a graph. Okay? This is called the period of a periodic function. Now again, for sine function, if the function starts here and it ends up here, this is one cycle, and the amount of time that it takes from this point to this point is called one period. The next definition is called a periodic function. This is the type of function that the y values, they have a repeating pattern. What exactly I mean is the following. Again, if you have a sine function like this one, let's say, you can see that the y values, they go up, down, up, down, and so forth. So all the y values, they are repeating. Now, how they are repeating is that there is a limit for maximum and minimum for the function. For the sine function, this maximum is 1, the minimum is -1. And we said before that the amplitude is the half distance between maximum and minimum. Okay? So this means that the function oscillates between maximum and minimum, which is 1 and -1. Anyway, a periodic function is a function which has a pattern of y values that repeats at regular intervals. Okay? That's a periodic function. Now, the definition of an amplitude, the formula. The formula is this one. Max minus mean divided by 2. So for any periodic function, if you know what is the maximum, what is the minimum, subtract them and then divide it by 2. That's going to give you the amplitude. Now, the amplitude of a function, remember, is a positive number. This means that, for instance, if I give you the function is -2 sine x, do not tell me the amplitude is -2. Amplitude is the absolute value. So you have to say the amplitude is 2. Amplitude is never negative. So the first example, I have two graphs here, A and B. You're supposed to look at the graph and tell me if it's periodic. And if it is periodic, you have to tell me what is the period of the function. So think about this. Okay, so the first one is periodic. Let's see why. If you look at this part of the graph and this part of the graph, you can see they are duplicating each other. This starts from here and goes up, down, up, and then to 0. The same thing happens to this guy. Now, to find the period, just find the difference between the time of the start and end. So 6 minus 0 is going to give you 6. So you say, yes, this is periodic, and the period here is 6 seconds. Now, this part is not periodic. The reason is that, for instance, this part is not repeated anywhere in the graph. So there is no way that this guy can be periodic. So the answer is no, so no period here. Okay, first question, is this a periodic function? Yes, it is, because if I take one branch of this graph, I can see that it's being repeated to the right and left, so this is periodic. Now, to find the amplitude, I'm going to find the maximum. The maximum is going to be 3. So the amplitude is maximum 3 minus the minimum is -1 divided by 2, which is 4 divided by 2, which is going to be 2. And the period, I'm going to find the width of one cycle. The width of one cycle is here, which is going to be 3 minus 1, which is going to be 4 seconds. Okay, the first thing is that the function is periodic, which is obvious because you are repeating the same cycle over and over again. What is the period of the function? Since this is one cycle of the function, I just find the distance between these 2 points, which are the minimum. And you can see the period is going to be easily 4 minus 2, which is going to be 6 seconds. So every 6 seconds, the function repeats itself. Now, just wait for part C or part D of the question. You will see the purpose of these periods, which is very important. The second part of the question says, what is the function, the value of the function at 2 and 5? The value of the function at 2, which is going to be here, which is going to be 1, as you can see. And the value of the function at 5 is going to be here, which is going to be 0. Next question is f of 8, f of negative 10, and f of 14. So I'm going to go back to the graph. Now the first one is f of 8. Since the function is periodic, although I don't have point x equal to 8, I can subtract or add the period and try to get inside this range, which is the period that I can see. So I can write that f of 8 is equal to f of 8 minus 6. Either you add or subtract the same multiple of period, you get the same point again. And this one is f of 2. Now I have point 2 here, which is going to give me equal to 1. Now, the next one is f of negative 10. I can write this guy as f of negative 10 plus 6. Again, you can add and subtract multiple of period, nothing happens because this is a periodic function. And this is going to give you f of negative 4. And if you look at the graph, you can see that f of negative 4 is going to be here, which gives you equal to 1. And the last one, f of 14, I can write f of 14 as 8 plus 6. Now, if I look at f of 8 here, no, f of 8 plus 6, and I can say that this one is equal to, I can see there, f of 8, but f of 8 can be written as f of 2 plus 6, which is the same as f of 2, because remember, the periods are repeating, the cycles are repeating. So this f of 2 plus 6 is the same as f of 2. And f of 2, as you can see from the graph, is going to be equal to 1. So all of them, they give you the same one. So the next one is, what is the amplitude of the function? Remember, the amplitude is equal to max minus mean divided by 2. Now, if we go back to the function again, you can see that the maximum happens here and the minimum here. The maximum is 3 and the minimum is negative 2. So if I plug it back in the formula, I'm going to get 3 minus 2 divided by 2, which is 3 plus 2 divided by 2, which is 5 divided by 2, which is 2.5. So that's the amplitude of the function. Okay, the next question, you're supposed to find 4 values for x such that f of x is equal to 2. So we are going to go back again to our graph, and we are going to find where the function is equal to 2. You can see the function is equal to 2 at this point. So we know at x equal to 0, the function is going to be 2. So if I add or subtract multiples of the period to 0, I'm going to get f of x equal to 2. So 0 plus 6 gives me 6. 6 plus 6 gives me 12. 0 minus 6 gives me negative 6, negative 12, negative 18, and so forth. So these are all the values that gives you f of x equal to 2. Okay, The first question, you have a graph of residential natural gas consumption in Ontario. First, why the graph looks like this one? The reason is that when we are at the beginning of the year, January, it's cold, so there is more gas to use. And as we get closer to the mid-year, it gets warmer, so we need less gas. And then when we go toward the end of the year, the amount of gas usage increases. So that's why you have a pattern which goes down, up, like the one which is shown here. The second part says, does this data appear to be periodic? The answer is yes. Although it's not perfect, but you can see that the same cycle is being repeated every year. Okay? Again, it is not perfect, but it's being repeated. Next part of the question, part C, says that assume the consumption of natural gas in Ontario can be modeled using a periodic function. Determine the approximate maximum value, minimum value, and amplitude of this function. To find the maximum, again, we go back to the graph and also the minimum. So if we go back to the graph, the maximum is going to be about 1.6 billion, which is about here. And the minimum we can take approximately to be 200,000. Okay? If we subtract these two and then divide it by 2, we can find the amplitude. So we can say the amplitude, A, is going to be 1.6 billion, because all of them are in thousands, so I'm just going to write 1,600,000 minus 200,000 divided by 2, which is going to give you 700,000. Okay, but again, this is in thousand, so it's going to be 7 billion, right? The next question is estimate the period of this function. Again, if we go back to the graph, you can see that every cycle, okay, starting from here, the beginning, to the end is one cycle, and then the next one goes from here to here, the second one. You can see that it takes 12 months, which makes sense because 1 year is 12 months, and this one is based on every month during the year. So the period of this function is going to be 12 months. So the period is 12 months. Now the next question is estimate the domain and range. Okay, the next question is estimate the domain and the range of the function. So again, we're going to go back to the function to see what are the valid x and y values. As we can see, x has to be greater than 0, and x is a real number. And the maximum y value is going to be about 1.6 billion. And the minimum y value is going to be about 200,000. So we can write the domain and range as d is equal to x in R and x greater than 0. And the range is y in R and y less than or equal 1.6 billion. Okay, and greater than or equal to 200,000, which is 2 billion. Okay, the last question is how can I use this graph to estimate the natural gas consumption in February 2011? So what we do is that we're going to go back to the graph. The graph gives you the value starting at 2001, and this one is 5 years. So it's going to give you the value of the gas consumption until 2006. If I want the value of the gas consumption in February of 2011, what I can do is that I can find the gas consumption for February and the second month for 5 consecutive years, and then I can get the average of all these consumptions, and that's going to be a good prediction of what the amount of gas consumption in 2011 is going to be, which is again not necessarily to be true, but it's going to give you approximate, how much gas is going to be used in 2011.